So let's talk about sodium now. And we're going to continue to use our hypothetical situation. There's a cell that is only permeable to sodium, and this is how we're going to understand the equilibrium potential for sodium. Okay? So again, we have ion distributions as in normal physiological conditions, such that there is sodium and chloride outside the cell, and there's potassium and those other negatively charged ions inside the cell. All right, so now because sodium is of a higher concentration outside the cell, and bear in mind this cell is only permeable to sodium, and potassium is at a higher concentration inside the cell, sodium now has a chemical driving force in what direction? Where does sodium want to go? Into the cell, perfect, into the cell. So it's higher concentration out of the cell, it wants to move along its concentration gradient into the cell. Okay, that's the first part of this here. The second part is that as sodium starts to move into the cell, what do we create? So sodium is positive, it starts moving into the cell, it's gonna leave behind that unopposed negative charge of chloride on the outside of the cell. And so what we have now is an electrical driving force. We have a separation of charge. Okay, so as sodium moves into the cell, there is now the establishment of an electrical driving force that wants to move sodium out of the cell. Okay, what do you think is going to happen now? If sodium keeps moving along both of these forces, what will eventually happen? We saw the similar thing with potassium. What will eventually happen if it's moving in equal and opposite directions? Right, it's going to get to equilibrium. It's going to approach equilibrium. Okay, so that's our next step. The cell eventually reaches equilibrium. And at equilibrium, all movement stops. Okay, the chemical driving force which wants to move sodium into the cell is now equally opposed by the electrical driving force that wants to move sodium out of the cell. And what is the number that represents this equilibrium potential? Positive 60. Okay, positive 60 millivolts. So at this voltage, at this membrane potential, sodium is no longer moving. It's at equilibrium. Okay, the flux that is moving inwards, according to the chemical gradient, and the flux that is moving outward, according to the electrical gradient, are now equal and opposite, and they cancel each other out. So this is how sodium reaches its equilibrium potential. Okay? And again, this is a hypothetical situation where we're looking at the specific equilibrium potentials of sodium and potassium. And this is going to help us understand how these two ions influence the membrane potential, or the resting membrane potential. So just to summarize here, there are two forces acting on sodium: chemical force, which wants to move it into the cell, an electrical force, which wants to move it out of the cell, and we get a net force, or an electrochemical force, that is stronger to the chemical force, but then the electrical force continues to increase. Okay? And we'll see how those balance out. All right, any questions so far? So we looked at the rest, we looked at the equilibrium potential for potassium. We said that was negative 94 millivolts. We looked at the equilibrium potential for sodium. We said that was positive 60 millivolts. And because these two ions are important in understanding the resting membrane potential, we're going to sort of blur these two equilibrium potentials together. Right? We're going to combine them and figure out where the resting membrane potential lies. So there's sort of 5 steps which we're going to walk through, 5 slides here, and these are the 5 steps, or the 5 processes that explain how the resting membrane potential is understood. The first step here is that we have chemical driving forces for sodium and potassium that are moving in opposite directions. Okay, we have a chemical force that wants to move sodium into the cell because sodium is at a higher concentration outside the cell. We have a chemical force that wants to move potassium out of the cell because it's at a higher concentration inside the cell. So we have these chemical driving forces on sodium and potassium. That's the first part of understanding the resting membrane potential. Okay. The second part here is that the membrane is understanding that the membrane is more permeable to potassium. What does that mean? We spoke about this before. What does that really mean when I say the membrane is more permeable to potassium? There are more potassium channels. Perfect. So as we can see on this cell, there are 3 potassium channels in blue and one sodium channel in red. So the membrane being more permeable to potassium means that potassium is going to leave this cell faster and in more quantity than sodium will enter. Okay? That's going to be very important for us to understand here. So now we have more doors, so to speak, for potassium to leave and less doors for sodium to enter. What will that eventually create? Right? If we're kicking more positive out, then we're bringing in what happens? The inside becomes more negative, right? More negative. We're kicking this positive charge out, right? We have more channels to kick potassium out than we have to bring that positive charge back in. And so the inside of the cell becomes more negative. That's the second step in understanding the resting membrane potential. Okay, everyone with me so far? Any questions? All right, step 3 is that we now develop an electrical force. Okay, because sodium was coming into the cell at a slower rate than potassium was leaving the cell, the inside of the cell is more negative than the outside of the cell. And so what we have is an electrical force at this point that wants to bring both ions back into the cell. Okay, I'll say that again. Because we had a situation, I'll go back here, we had 3 potassium channels, 1 sodium channel. Potassium is leaving faster than sodium is coming in. All right, the next step here is that the inside of the cell is more negative, and now both ions want to move along an electrical gradient to come back into the cell. All right, so because sodium is positively charged and potassium is also positively charged, they both want to get back into that negatively charged cell. And so the electrical driving force of these are both moving into the cell, right? Now the difference here is, and this is pretty important, potassium is going to flow out slowly and sodium is going to flow in fast, right? Why is that? Why is that? Who can tell me why that is? Why will potassium move out of the cell slowly or trickle out of the cell, whereas sodium is just flushing into the cell? Why is that? Look at this image and think about why sodium would be moving much more fast into the cell and potassium is trickling out. This ties back into something we spoke about earlier. When we have 2 forces, what do? We add those 2 forces together, right? If they're in the same direction, then those forces will amplify, right? So here we have a chemical driving force for sodium moving into the cell. We have an electrical driving force for sodium also moving into the cell. And so we're going to really combine those 2 forces, and that is going to amplify the strength with which sodium wants to move into the cell. Why? Because it's in the same direction. So the chemical driving force and the electrical driving force are in the same direction here. And so we have a magnified amplified strength of this electrochemical driving force. Potassium, on the other hand, its electrical driving force is in the opposite direction of its chemical driving force. And so it's going to be opposed. It's going to be sort of slow and sluggish to leave the cell because it has a force that is opposing it. Okay, it's not going to go out of the cell as quickly as sodium is rushing in. Okay, that's very important to understand here. Any questions on this? So at this point, sodium is going to continue to move into the cell, potassium is going to continue to move out of the cell, And they're going to get to a point where they sort of balance each other out. And this is what we call steady state. Steady state means that the inflow of sodium is balanced by the outflow of potassium. Okay? And I'll explain what that means really. So we said that the membrane is more permeable to potassium and less permeable to sodium. But sodium is coming in faster and potassium is rushing out slower. Okay, so those two actions are going to balance each other out. If you have lots of doors for potassium, but it's really crawling through those doors, and you have very few doors for sodium, and it's rushing through that one door, those two forces will eventually balance each other out. What is the membrane potential when those two forces balance each other out? What is the membrane potential? What's the figure when those two forces eventually balance themselves out? Negative 70 millivolts, thank you. So that is the membrane potential, right? That's the membrane potential inside the cell. That's the voltage inside the cell when a neuron gets to steady state. And just to reiterate here, steady state is where the movement of sodium and the movement of potassium cancel each other out, balance each other out, okay? And that is because sodium is rushing in through this one door, it's less permeable, and potassium is sort of trickling out through these many channels or these many doors, okay? And this is how we establish the resting membrane potential. So a neuron that's just chilling out, it's not doing anything, not excited, has a resting membrane potential of negative 70 millivolts. And that is brought about by the movement of sodium and potassium when they get to steady state. Any questions so far? Okay, let's keep going. Now it's important to understand that the sodium-potassium pump here is vital, is crucial in establishing this resting membrane potential. The sodium-potassium pump, as well as these leak channels. Bear in mind that these channels are leaky ion channels. So they're what type of transport? Passive transport. So these do not require energy. The sodium-potassium ATPase pump does require energy. This is active transport. So what's happening is the sodium-potassium pump is going to pump 3 sodiums out of the cell, right? Actively using energy. And then those 3 sodiums are going to seep right back into the cell or leak right back into the cell through this leaky ion channel. It's going to kick or pump 2, what did I say, sodium? Pump 2 potassium into the cell, and then those 2 potassiums are going to leak right back out of the cell, right? They're going to do so much more easily simply because there are more potassium channels. The membrane is much more permeable to potassium. All right. So to sort of summarize all of that, the resting membrane potential is closer to the equilibrium potential of potassium. Why is that? Why is the resting membrane potential, why does that number look more like the equilibrium potential for potassium? Why is it more negative? Why is it similar to potassium's equilibrium potential? Can anyone think of that?
Because the membrane is more permeable to...
It is, and it's perfectly correct. So the membrane is more permeable to potassium, and so the movement of potassium is going to look very similar to the resting membrane potential. Alrighty, and so because the equilibrium potential for potassium is negative 94 millivolts, and the cell is more leaky to potassium, so to speak, at rest, the cell is negative 70 millivolts, which is very close to potassium's equilibrium potential. Not so much to sodium, and sodium is very, sodium's equilibrium potential is very positive. It's 60 millivolts positive. Okay, so it's very far away. And this also represents the force with which sodium wants to come into that cell, right? But it cannot do so easily. Why? There are less what? Channels. There are less ion channels here. So sodium has a strong force to get back into the cell, but it cannot do so easily. There are less channels. Potassium, however, has a weaker force to get into the cell, to get out of the cell, and it can do so because there are much more ion channels.